Hello everyone, and welcome to the fourth and final video for our Class 8 series of lecture videos. And it will be a short video, but still some interesting information to point out, because now we're going to consider the kinetics of the reaction. So we might ask, what's the rate determining step for our radical chlorination of methane? Well, it turns out that it's the first elementary step in forming the methyl radicals, since the energy barrier for that step is highest. The rate equation for chemical reaction is always written from the rate determining step, and so since we're the first elementary step in that chlorination of methane, we can write our rate from that elementary step, and it's some rate constant K that's temperature dependent, multiplied by the concentrations of the reactants, so the concentration of the chlorine radical and the concentration of methane. So if you wanted to, say, speed up your reaction, you would increase either the concentration of your chlorine radical or your concentration of methane, or you could, in theory, increase both. Of course, since the reaction is carried out in gas phase, you could think about increasing pressures to increase concentrations. At any rate, another interesting bit of information I'd like to point out has to do with the thermodynamics of various halogenations. Table 3.4 in your text outlines halogen dissociation variables or values. For a given halogen, which we often symbolize as X in organic chemistry, our diatomic X2, we have different dissociation values in kcals per mole for these bonds. And it's kind of interesting, there really isn't a periodic trend here. Diatomic fluorine is very low, 38 kcals per mole, and chlorine, diatomic chlorine, is relatively high. It's the highest amongst these halogens at 58 kcals per mole. Then bromine, diatomic bromine's dissociation energy is 46 kcals per mole, and then iodine's dissociation energy is 36 kcals per mole. So table 3.5 shows changes in enthalpies for the propagation steps in the halogenation of methane, and I think it's kind of interesting to go over these because they have interesting implications for how practical any of these halogenations is. The changes in enthalpies, of course, are given in kcals per mole. I have not written the units on these values. However, what I'd like to point out is for our first elementary propagation step, which was the rate limiting step in the chlorination of methane, for which we had a slightly endothermic value in terms of delta H. For radical fluorination, it's exothermic, that first step. And for bromination, we simply get more endothermic, and then iodination is very endothermic. In the second step, which helps redeem our radical chlorination by making the overall reaction exothermic, we release 27 kcals per mole. For radical fluorination, it's even greater at minus 72 kcals per mole. So radical fluorinations are very difficult to control. If you start fluorinating something in a radical manner, it's going to be very difficult for you as a scientist to control that. If you want to achieve monofluorination, you might choose a different type of reaction mechanism than radical fluorination. Another interesting point is that for bromination, we're getting less exothermic overall. And then finally, by the time we hit radical iodination, our overall change in enthalpy for the reaction is positive, so that's endothermic. So in practice, chemists typically do radical chlorinations and brominations. If they want to be selective, they can certainly do radical fluorinations, but they're going to lose selectivity, and we'll see that in our Class 9 series of lectures. And for most purposes, organic chemists don't do radical iodinations. We find alternative ways to incorporate iodine into our organic molecules when we need to. So that pretty much concludes the fourth video for our lecture class time. And I'll see you in the ninth class time session.